Hi, we're going to continue our lesson on the United States history of apportionment with the U.S. House of Representatives. So in the last video, we talked about the Hamilton's method, but it violated the quota rule, and it also violated the Constitution for a couple of specific House sizes. So after George Washington vetoed that bill, Congress quickly passed a new bill that uses what we'll call the basic Jefferson method. And actually this method was used for another 40, 50 years or so, as we'll see shortly. So before we get into that one specifically, there are two methodologies for apportioning the House of Representatives. There is the basic divisor method, the modified divisor method. And in the basic divisor method, the House size, the size of the House of Representatives, is the result of this method. Modified divisor method, the House size H is the goal. We want the House size to contain 200 members. You would use the modified method. If you don't care what the House size is, as a result, you use the basic. And thirdly, the quota method, which we've already talked about, the Hamilton method. That's one quota method. The House size H is the resource. You use the House size to then create the quota. All right, so the basic Jefferson method is decide on a divisor. And again, that divisor is the number of people each representative will represent. Calculate each state's quotient. The quotient is the population divided by the divisor. And don't forget, this divisor, at least according to the U.S. Constitution, cannot be less than 30,000. It has to be greater than 30,000. The state's apportionment is rounded down, and the resulting House size is the sum of the state apportionment. So this is the basic Jefferson method, and we're using a min or rounded down method. So this is what I mean going back here, why the House size is the result. At the end of this method, then you get the House size. So if we look at a couple examples, this method was then applied to 1790. S is the number of states. There are 15 states in the Union. The divisor was 33,000. So they let each representative essentially represent about 33,000 citizens. And in that time, the initial House size was 105. I think it's pretty interesting. 10 years later, one new state was added to the Union, same exact divisor, but look at that, 36 more representatives. Obviously, the population went up also. And then in another 10 years, 1810, another state was added. The divisor was actually increased. So each representative represents more people. And the House size still increased. In 20 years, 76 representatives. And as it goes on, we're looking at the ratio of representation, that's that divisor, and the House size. So this basic Jefferson method, problems were discovered both at the beginning and then later on. One of those issues is that Jefferson's method systematically favors large states. So again, don't forget that large state would be a state like California, large population states. And it can violate the quota rule, meaning a state, and usually the large state, should get a larger or more than fair share of representation. So that Jefferson method was used, though, from 1790 to 1830. And right around this time, kind of debate started popping up on the apportionment. And three new methods were proposed to deal with the decimal part of the state's quotient. All right, so Jefferson method, this was the method that had been used the last 30, 40 years with the round down method. Now, John Adams was a politician, eventually became the president. He did not like this. He had a lot of problems with this method. A lot of his arguments had to do with the big states getting more representation. He thought the smaller states should get a larger share of representation. So he argued that we should round up. Just take those decimals, and if the part was 5.2, then you give that state 6 representatives. Just always round up. His philosophy was more representation is better. All right, and at this time, one of his good friends was Daniel Webster. And Daniel Webster happened to be the chair of the Senate Apportionment Committee at the time. So there's many letters that we have from Adams writing to Webster saying that how much he didn't like the Jefferson method. He proposed his roundup method. Around the same time, James Dean, and this is a man after my own heart because he was not a politician. James Dean was a mathematician. He was a math professor at the University of Vermont. And this debate was going around. He was not a politician, but he was still interested in the debate. He proposed that you round the number up or down according to which option gives the state's constituency. Again, this is the number of people per number of people per representative. He said you should round up or down according to which gets closest to the divisor. All right, now, while this is going on, Adams' good friend Daniel Webster, the consummate politician, said, this is why you're rounding up, why you're rounding down, what is this weird round up or down according? I've been rounding since I was a kid. Let's just round normally. If it's above 0.5, we round up. If it's below 0.5, we round down. So right now, there are 4 methods up for debate. Jefferson method currently in use. Adams proposed round up. Dean proposed this kind of strange round up or down on a state-by-state basis, and Webster says round normally. All right, so just to connect this with our average lesson we talked about went over last week, Jefferson's method basically is saying take the mid-rounding approach. Adams says take the max rounding approach. Webster, the round normally, that's what we call arithmetic rounding. And strangely enough, we'll talk about this later, Dean's proposal, round down or up to get closest to the divisor, is actually the harmonic mean rounding, that strange third rounding we talked about. So let's look at an example of what James Dean was trying to propose. Again, this was the mathematician that made this proposal, and he said that round the number up or down in the state-by-state basis. So in 1930, the U.S. population was almost 12 million, 11,900,000. And just for one case, let's suppose we want the constituency to be 50,000. So again, this means each congressman or congresswoman will represent about 50,000 citizens in their state. And let's take Vermont as an example. Vermont's population at the time was 280,000. So if we divide Vermont's population by 50,000, we get their quotient Q, 5.613. So then the issue becomes, does Vermont get 5 or do they get 6 representatives? It has to be one of those two if we're going to satisfy that quota rule. All right, so the Jefferson method says round down, 5 seats. That's what was in use. So Vermont at this time had 5 congressmen. Adams' proposal was to round up. Just move that 5 up to 6. And notice Webster would also say to round up because 5.6 is greater than 5.5. But I want to focus on this weird Dean's method, James Dean. So notice if you take Adams' proposal with 5 seats, the constituency is 280,000 divided by 5. So in Vermont, each representative would represent about 56,000 citizens. And if the state gets 6 seats, 6 House of Representatives, you take the population divided by 6, each single congressperson would represent 46,776. So again, this is why Adams wanted more round up. You get more representation, or each representative represents less people. So Dean would argue that 46,776 is closer to 50,000. Right? Those are off by 3,200 and something. Whereas if you take 56,000, you're off by 6,000. So since this number is closer to 50,000, Dean would say give Vermont 6 seats. Again, not because we're rounding up, not because of the 0.6, but because the constituency is closer to the goal. Okay, so for James Dean's situation, technique, select the constituency. In the last example, this was 50,000. Calculate the quotient, that's population divided by constituency. N is just the integer part. And again, you were going to round to either n or n plus 1. So Dean said the constituency should be the target. There's a target right here. And we're going to look at the population divided by n, the population divided by n plus 1. Right? This is going to be smaller. So population divided by 5, population divided by 6. Which one of these two is closer to the goal of, let's say, 50,000 in the last example? And a kind of strange thing happened. And James Dean, a math professor, as far as we know, did not know this. His method is mathematically equivalent to you round up if that quotient is greater than the harmonic mean, that third and strange way of averaging we talked about before. So I want to go over this. So I want to talk about how does this strange approach equal the same as the harmonic mean. So I want to go through this, but don't worry too much about the details. I will post these slides if you are interested to go through this more slowly. But James Dean said the A apportionment should be the bigger number, round up, exactly when this distance, the divisor minus the population over n plus 1, is less than or equal to the population divided by n minus d. So if we do a little bit of algebra, this is adding b to d to both sides of the equation and adding p over n plus 1. Do a little bit of algebra right here. Then we could factor out p as the proportion. And if we divide both sides by d and what's in the parentheses, we get this 2 over 1 plus n plus 1 over n plus 1. There is the harmonic mean. And the population divided by the divisor, that is the quotient. So I got the harmonic mean and the quotient. So Daniel Webster said this is way too complicated. What are you guys talking about? Why don't we just round normally? He said round up to the next largest whole number, only if this quotient is bigger than the arithmetic mean. So this is just the normal rounding. So just to kind of look at a visual, here's Dean's approach. D is the target. What actually happens with Webster, you take the inverse of all of these values, and instead of D being the target, 1 over D is the target. Kind of a strange thing happens. So there's I think a kind of an interesting irony happened with Daniel Webster versus James Dean's two proposals. For one, James Dean was a math professor, but his proposal that he gave to the Congress at the time was given due to political reasoning. And the reason is Dean's target is D. The target is the number of people per congressman. If you take the inverse of this, Webster's proposal to take the arithmetic mean actually turned out to be the opposite of that, is looking at the target is the congressman or congresswoman per person. So kind of flipping these two values. Again, Dean's looking at, he wants the targets to be how many people should each congressperson represent. And Webster was saying how many people should, how many congressmen or congressmen or women should there be per person in each state. So Dean was a math professor who made a proposal due to political reasoning and strangely was not aware of the mathematics of this proposal, of that arithmetic mean. Daniel Webster was a consummate statesman. He was a lifelong politician, and he proposed a simple mathematical formula or calculation to create the apportionment method. And he was completely, as far as we know, unaware of the political implications of his method. Okay, in the next video, we're going to go over how to compute Dean's and then comparing what happens using these so far 4 methods.